Today we explore functional limits and continuity, starting with the precise epsilon delta definition, then working a full proof, then a removable singularity, and finally a classic example of a limit that fails to exist. Here is the idea in words. We say the limit of f of x as x approaches c equals L if for every positive tolerance epsilon, no matter how small, we can find a positive distance delta, such that whenever x is within delta of c, but not equal to c, the value f of x is guaranteed to be within epsilon of L. Let's put this to work on a concrete example. We will prove that the limit of x squared as x approaches 3 equals 9 using the full epsilon delta method. On screen, picture the curve of y equals x squared, shown first in a clean two-dimensional view, then as a fuller three-dimensional surface breakdown, with the same running caption updating in place as we go. Our goal is to make the quantity x squared minus 9 as small as we like by controlling how close x is to 3. We factor this difference as the product of two simpler pieces, x minus 3 times x plus 3. Now we need to control the size of x plus 3 near x equals 3. If we agree to only look at x values within 1 unit of 3, then x plus 3 stays trapped between 6 and 8, so its size is bounded by 7. This means the size of x squared minus 9 is at most 7 times the size of x minus 3, so if we want this product smaller than epsilon, it is enough to make the size of x minus 3 smaller than epsilon divided by 7. So we choose delta to be the smaller of 1 and epsilon divided by 7. Whenever x is within this delta of 3 but not equal to 3, the value of x squared lands within epsilon of 9, exactly as the definition demands. Check step, try epsilon equals 0.7, then delta becomes 0.1. Picking x equal to 3.05, well within that delta, gives x squared approximately equal to 9.30, which indeed sits inside the epsilon window around 9. That completes the first principles proof. Now let's switch to a genuinely different route to the same result, the sequential approach, which uses sequences instead of tolerances directly. Here is the alternative argument. Take any sequence of numbers that approaches 3 as its limit. By the product rule for limits of sequences, the sequence formed by multiplying each term by itself must approach 3 times 3, which is 9. Since this holds for every such sequence, the functional limit of x squared at 3 must also equal 9, confirming our earlier result through a completely different logical path. Check step, take the sequence 3 plus 1 over n. As n grows large, this sequence approaches 3, and squaring each term gives a sequence approaching 9, matching our proof. Now let's move to removable singularities. Consider the quotient x to the power n minus a to the power n, all divided by x minus a. At first glance this looks undefined right at x equals a, because both top and bottom vanish there. But the numerator factors completely. It equals x minus a times a polynomial made of descending powers of x and ascending powers of a. Dividing by x minus a cancels that troublesome factor exactly, leaving behind a smooth polynomial with no division problem anywhere. This means the original quotient extends continuously to x equals a, taking the specific finite value, n times a to the power n minus 1. On screen, show the punctured curve in 2 dimensions first, then the same surface in 3 dimensions, with the single missing point now filled in smoothly at that value. Check step, let n equal 2 and equal 3. The quotient simplifies to x plus 3, which at x equals 3 gives 6, matching n times a to the power n minus 1, since 2 times 3 equals 6. Now let's look at a function that behaves very differently near a point, sine of 1 over x, at x equals 0. Show this oscillating curve in 2 dimensions, then unwrap its infinitely rapid wiggling near 0 in a fuller 3-dimensional view, keeping the same caption in place. Choose one sequence approaching 0, namely 1 divided by n times pi. Plugging into sine of 1 over x always gives sine of n times pi, which is 0 every time, so this sequence forces the function toward the value 0. Now choose a second sequence approaching 0, namely 1 divided by 2 pi n plus pi over 2. Plugging into sine of 1 over x always gives sine of pi over 2, which is 1 every time, so this sequence forces the function toward the value 1. Since two different sequences, both approaching 0, produce two different limiting values, 0 and 1, no single limit can possibly exist for sin of 1 over x at 0. The function oscillates too wildly near that point for any one value to capture its behavior. Now contrast this with a closely related function, x times sine of 1 over x. Even though sine of 1 over x still oscillates wildly, it is always trapped between negative 1 and 1, so the whole expression is squeezed between negative x and positive x. As x approaches 0, both of those bounding curves shrink to 0, so by the squeeze principle, x times sine of 1 over x is forced to approach 0 as well. Unlike its cousin, this function does have a well-defined limit at 0. Check step. At x equal to 0.001, the value of x times sin of 1 over x lies somewhere between negative 0.001 and 0.001, confirming it is being squeezed tightly towards 0, exactly as the squeeze principle predicts.